All right. Hello, everybody. I know it's kind of funny. We are in a virtual class, so you are virtually with me, behind me on this side and that side. I don't want to move a lot, or some parts of my body will disappear, like this. Okay. So let's get started. Let me get a chair, an invisible chair that becomes visible in a few seconds. Okay. So share my screen with you. Okay. So now you can see me up here, which is good. Or not. I don't know. Is this side okay? Let me make sure. Yeah, I should be fine. Alrighty, I put myself up there. Hopefully you can hear me well and you can see me up here. So I guess the materials will appear here and here. All right, anyway, let's get started. We are working on part 3 of mobile equipment power, rolling resistance. So let's get started with the definition. We need to, in this chapter, we need to know the definition of two things, being the rim pull and the drawbar pull. Okay, these are the two important factors an equipment can provide. Those actually two important forces an equipment can provide, and they actually show how powerful piece of equipment is. Okay, so let's see what each one is. Starting with rim pull effort. Rim pull effort, it is the force. So when the machine wants to stop moving on a surface, okay, the tires should exert or should apply some force on the surface, okay, and if that force is enough, then the machine will start to move, okay. So rim pull is the force exerted by, rim means the outer edge, right? So rim pull force is the force exerted by the outer edge of the tires to the surface of the earth, and which makes the machine move. Okay, so that's rim pull effort. But what is the drawbar? So pull available at rim of each driving wheel. Okay, that's another simple definition for rim pull rim pull effort. Sorry. So drawbar pull is the pull force available from a vehicle. Means how much load can a vehicle draw, okay, or it can pull. That is the drawbar pull. So to measure drawbar pull, you can tie a rope, okay, let me get my pen here, okay. Oh, okay. So you can tie a rope to the center rear of the vehicle. Let me challenge my driving. So if this is a vehicle without moving your pen from the paper, okay, and it is drawing, and let's say you are measuring the force here, okay, you're measuring what is the power, what is the force, what is the drawing force, what is the pulling force of that vehicle. The pulling force of a vehicle is called the drawbar pull. Okay, so far so good. Rim pull is the force the tires will apply to the surface so they can move the car, they can move the vehicle, the equipment. And drawbar pull is the pull force of an equipment, okay? Means what load an equipment can pull is the drawbar pull of that equipment. Okay, now let's get into more details about each of them. So rim pull. What is rim pull again? It is the tractive force, okay? The tractive force between the tires of a machine and the surface on which they travel, okay? So this is what I just said. This is the force that the tires will apply on the surface to make the machine move. So how does tire slippage happen? So sometimes, as you've seen, the vehicle wants to move, but there is a slippage. I mean, the tire rotates at its place without making the car move. That happens because the coefficient of traction is too low. In fact, the coefficient of traction should be high enough to make the car move. I mean, so that the force it applies, the tires apply on the surface, will be enough to move the car. Okay, so we'll talk more about coefficient of traction today in a little bit. What does maximum rim pull depend on? So, it depends on two factors. Number one is the power of the engine. So obviously, the more powerful is your engine, it can move the car better, right? So it is directly related to the power of the engine. It is also related to the gear you're moving with, okay? So can you make a guess which gear? Is it the first gear, the lowest gear, or the highest gear that provides the maximum rim pull force? As most of you have probably guessed, the lower gears, actually the lowest gear, generates the maximum rim pull force. And as you change the gear to higher ones, the rim pull force decreases. All right, how much is the maximum effort rim pull when the driving wheel slip on the supporting surface? So the maximum effort in that condition is the total pressure the tires exert on the surface, okay? So that is the total pressure multiplied by the coefficient of traction, okay? So if you multiply that power by the coefficient of traction, you can get the rim pull effort. There is another item that is also important in the rim pull force of a vehicle, and that is the speed of the vehicle. I'll talk about it in a little bit. What unit of measurement do we use for rim pull? We use pounds, okay? So pounds is the unit of measurement. Pound is the unit of measurement we use for measuring the rim pull force. Okay, now, how to compute it? Rim pull, like I said, it is directly related to the power of the engine, okay? The power of the engine is measured with horsepower, right? So the more powerful your machine is, the more rim pull force it can create. So efficiency is another factor, and efficiency is most of the time given to us. It ranges from 0.8 to 0.85 in most cases. It will be given to us, and like I mentioned earlier, it also depends on the speed. I mean, it is inversely connected with the speed. I mean, the faster you move, okay, the less rim pull you will get, okay? And you all might have experienced this. So imagine you want to start moving your car on a very slippery surface, like on snow. On a snowy day, you start your car, you start your engine, and you want to move. If you, hit the gas pedals, too hard, it means if you want to move with a lot of speed, most of the time, your tire will slip on the ice, okay? Because a lot of speed will create less rim pull effort. Does that make sense? So in order to create a higher rim pull force, you should go more slowly, okay? That is the rule. Speed and rim pull effort are vice versa. Okay, like I said, the efficiency of most tractors and trucks will range between 0.80 to 0.85. Okay, and SAE recommends using 0.85 when the efficiency is not known. So in a problem, if you don't see, if they don't give you the efficiency, the default is to consider as 0.85. Okay, let's do an exercise together. Let me see if I can move myself. Okay, just did that. Assuming that the coefficient of traction is sufficient, that the truck's total power can be developed, calculate the rim pull of a pneumatic tire truck with, okay, so the power of the engine is given and the speed is also given. So that's two factors we need because the coefficient, let me show it, the efficiency, if it is not given, you can consider it is 0.85. So the speed is given here in the problem we have, and the power is given. So you can find this guy. Let's go ahead. This is the formula we use. 375 is the constant. Okay, it is fixed in all the problems. 140 is the horsepower of the machine taken from here. Okay. And 85, like I said, is the default when it is not given to us. It's the default for efficiency. And of course, 3.3 is the speed of the vehicle. So this is the power of the machine. Okay, this is the power that the tires are applying on the surface to make the machine move. Okay. So if the manufacturer tells you that in each gear, what is the speed the machine can generate, okay? Just forget about the rim pull and all of these things. Just consider the manufacturer has told you with gear 1, the machine can get a speed of 3.3, with gear 2, like 5.7, and so on and so forth. Yeah, for example, this to the left is given by the manufacturer. You know, in the first gear, this is the speed you can get, second, third, fourth, and fifth. So by moving these numbers, instead of 3.3, you can find the rim pull for different gears. So if we just did the first one, as you can see, here's the first one, and according to the changes in the speed, you can find the other ones. So as you can see, as the speed goes and as the speed increases, so if this is the speed, by this I mean from going from little to much, okay, the rim pull decreases, okay. So rim pull, as you can see, with the first gear, you got the maximum rim pull. And with the fifth gear, where you got the maximum speed, you got the lowest rim pull. That's how it works, okay? Remember the example of moving the car on a snowy surface. So computing the speed the machine can get. This is also very important, okay? Because if you know the rim pull, let me go to this equation. If this is known, okay, so let's say this is known, and the efficiency is always known, you can, if it is not, you can just assume it to be 0.85, and the machine horsepower is also known. So by having those pieces of information, you can get the speed of the machine, okay? So if you have the rim pull force, you can say with that rim pull force, your machine can obtain a speed of blah, blah, okay? So that is also important and very practical. Using that equation, you can get the speed of the vehicle, of the equipment. Okay, but there is one important thing to consider, and that is not all of the rim pull effort can move the machine, when we talk about the ripple effort, our assumption is that we are moving on a level surface, no grade. We're not going up, we're not going down. It is level and there is no friction, okay? So in fact, we are not considering, we didn't consider the grade resistance and the rolling resistance. But in the real world, the grade resistance, I mean, let's say you want to move up a hill, okay? Your machine wants to go up a hill. So you should, first, you should defeat the grade resistance, and there is rolling resistance. So in fact, a portion of the ripple force will be consumed for defeating the total resistance. And total resistance is nothing but the summation of the rolling resistance and the grade resistance. So to wrap it up, the effective ripple force is the total ripple force minus total resistance. And the total resistance, so the usable ripple force is the ripple minus rolling plus grade resistance, okay? Plus grade resistance. All right, let's do one example together. So I move myself down, okay? A 12.4 ton tractor, okay? So we have the weight, has a maximum ripple of, okay, so the ripple is given in the first gear. Does it help here? No, because no table of different gear is given to us, but that's just some information. If it is operated on a haul road with a positive slope of 2%, so there is some grade resistance, and the rolling resistance of 100 pound per ton. If you remember, that's the unit of measurement for rolling resistance, pound per ton, US pound per ton. So what will be the power available for towing a load? Let's see. First of all, not all of the force the machine can generate can be used to move the car. So a part of it should be used to overcome the total resistance. So the pool available for towing the load will be maximum ripple, but some of it will go for the grade resistance. The grade resistance, if you remember from previous classes, was the weight of the machine, okay? The weight of the machine, if my pen writes, okay? The weight of the machine multiplied by 20 multiplied by the grade, okay? This is the grade resistance. So remember, this is the grade resistance. Now, what is the second item we need to find? We need to find the rolling resistance. The rolling resistance is the weight of the machine, okay, multiplied by 100, and this is what it is. Both of them are in pounds, so they could be summed. They could be added to one another. So the total resistance is the summation of these two guys, okay? So let me fix my camera and I'll be back in a minute. Alrighty, I guess I could fix the issue, so let's go back to the problem we're doing. Alright, so so far we have the total resistance and we have the ripple. So the difference between the two of them would be the power available for towing a load, okay? The difference between the total rim pull, the maximum rim pull, the maximum rim pull, and get my pen back, the maximum rim pull, and the total resistance. Okay, so let me pull myself up. So yeah, this is the maximum rim pull minus the total resistance. All right, so let's move on. Next thing we need to learn, get my pen, is the drawbar tool. If you remember, drawbar tool is the power of the machine in towing a force, okay, in towing something, a load. So how much force it can apply to a load when it is drawing it, okay? Let's say the machine is pulling or is drawing a load. What is the maximum force or what is the maximum load it can draw? So what is the draw pull? The draw pull is the towing force of a crawler tractor. Tractor. So this is important. We're talking about a crawler tractor, okay? It means we're not talking about the tires, okay? It is a crawler tractor. If you remember, these are the crawler tractors, okay? I mean, they don't have tires. So this is the power they could apply to a load. How is the drawbar pull available for towing a load computed? How is it computed? It is computed by subtracting the force required to overcome the total resistance, okay? So you should not consider the force that we need to overcome the total resistance and imposed by the Hall conditions from the total pulling force. So the total pulling force minus the force you need to overcome the total resistance will give you the drawbar pull force. So go up now. How does the grade impact the drawbar pull? You can make a guess, right? So if you want to go up, can you draw a load as easily as you would on a level surface? Obviously not. If you want to go up and draw a load, you would have to, consume more energy. It's because you should overcome the grade resistance. So to make it easier for ourselves, we consider that if a crawler tractor tows the load up a slope, its drawbar pull will be reduced. It means its power will be reduced by 20 pounds for each ton of weight for each 1% of the slope. Okay? So you can actually create an equation for this. So it will be reduced by 20 pounds by each ton of weight. For example, if it is 10 pounds, if the machine is 10 pounds, and if the grade, 10 tons, okay. If the machine is 10 tons, and if it is going up a hill with 5% grade, okay, with 5% grade, for each 1%, it is like this. So you should have 5 of this, okay? 10 multiplied by 5 will give you 50. So 50 will be reduced from the maximum drawbar tool it can generate in this example. Well, there's a better example in the next slide. What unit of measurement is used for drawbar tool? Again, pound is used for that. Yeah, it is measured in pounds. Alrighty, so in testing a tractor to determine its maximum drawbar pull at each of the available speeds, the haul road is calculated to have a rolling resistance of this much, 110 pounds per ton. Okay, this problem, okay, if a tractor is used on a haul road whose rolling resistance is higher or lower than 110 pounds per ton, the drawbar pull will be reduced or increased, okay? So, respectively, what does it mean? It means if it is higher than 110 pounds, okay, it will be reduced. If it is lower, it will be increased, okay, by an amount equal to the weight of the tractor in tons multiplied by the variation of the haul road from 110. What does it mean? Okay, let me give you an example. So let's say the rolling resistance we have is 150, okay? So how much more, what is the distance between 110 and 150? That would be 40, okay? So by an amount equal to the weight of the tractor in tons multiplied by the variation. And for example, if this tractor is 10 tons, okay, then 400 pounds of the drawbar tool should be reduced from the original power. Okay. If you didn't understand, don't worry. I'll just give you another example. So a track type tractor whose weight is 15 tons has a drawbar pull of this much in the sixth gear when operated on a level road. When it says on a level road, it means the total resistance is just the rolling resistance because the grade resistance is 0. Okay, of 110 pounds. If the tractor is operated on a level road having a rolling resistance of 180, remember the golden number was 110. Here we're dealing with 180, which is 70 pounds per ton more than the golden number for rolling resistance. How much the drawbar will be reduced? So can you guess the answer? That is the difference between 180 and 110. Okay, so the difference between 180 and 110 multiplied by the weight of the vehicle, which was 15 tons. Okay, so this much should be deducted from its maximum drawbar pull. Okay, so the drawbar pull was this much, but this much will be consumed for overcoming the rolling resistance. In fact, once again, the total resistance here is just the rolling resistance as the grade resistance is 0. Okay. All right. Drawbar, pull, and the speed of the vehicle. Maybe I just put myself here. Okay. The drawbar pull of a crawler tractor will vary indirectly with the speed of each gear. Remember when we did the rim pull example and we said the faster you go, the less rim pull force the machine can generate? We have the same story about the drawbar pull and the speed. It means the faster you go, the less drawbar pull you can get. So if you are hauling another car with your car, okay, if you want to go super fast, then the pulling capacity of your car will decrease. The slower you move, you can generate a higher pulling capacity with your vehicle. That's how it works. It is highest in the first gear, as you can see. As the speed is low, the first gear has the highest drawbar force, and the highest gear has the lowest. So highest is for drawbar pull is for the lowest gear. Okay, so therefore attainable speed is limited by the required pounds of pull for a specific resistance condition, and the specifications supplied by the manufacturer should give you the maximum speed and drawbar pull for each of the gears. Yeah, usually that is provided for the users, okay? If you rent a machine or if you buy it, the manufacturer will tell you for in each gear, and we are not talking about the trivial points of equipment. These are very practical, very fundamental, information. You should know to use an equipment, a piece of equipment, more effectively. So remember, they provide you with a table. In that table, they will give you this information that for each gear, what is the rim pull and what is the drawbar force the machine can generate. Then, according to that, the operator should adjust the gear and the machine's power based on the need, based on the load they are towing, or based on the surface of the road, the grade resistance, and the rolling resistance. All right, so usable power. What is usable power? Usable power depends, as implied by the name, that's the power, that is the part of the power that is actually doing the work, okay? Because a part of it is for overcoming different forces, okay? Different resistance. So the part that actually gets the job, does the job, is called the usable power. That depends on three factors. Obviously, surface condition is a big factor, okay? If you're working, and by surface condition, we mean both rolling resistance and grade resistance. If it is level, or if there is a grade, or if it is soft, or if it is tight, if the machine is moving on a compacted surface, which is very stable, or on a very soft surface, okay, and other factors. So surface conditions, the first factor. Second condition, or the second factor, is the altitude. You might ask, how does it impact? So can you guess what happens in very high altitudes? Very high altitudes, there is less oxygen, so the power the engine can generate, the combustion in the engine, can be affected by the altitude. So at very high, you might ask, will we do construction work in high altitudes? Oh yeah, we do that. Okay, there are lots of examples of construction in very high altitudes in the mountains, and in those areas, the productivity of the machine could be impacted by the altitude. And the third factor that could impact the usable power is the temperature. In very hot temperature, there is a reduction in the machine's productivity. So, like I said, an increase in altitude will reduce the power of a four-cycle engine about 3% for each 100,000 feet. Okay, so if in a problem they tell you you're working in 200,000 feet, then whatever power you have should be reduced by 6%, right? If it is 2,000. For the first 1,000, you lose 3%. For the second 1,000, you will use another 3%. So a total of 6% will be reduced from the power. How does temperature affect usable power? Like I said, in high temperature, the engine power will be reduced at a rate of 0.9, so that's a very marginal impact, a lot less effective than the altitude's impact. So that was 3%. Here it is less than 1%. It is 0.9% for each 10 degrees of Fahrenheit. Okay, cooling. Fahrenheit. Cooling has a reverse effect. So, for example, if the machine has a certain, power at, let's say, 72 degrees of Fahrenheit, okay, and if 72 changes to 92, okay, sometimes this can happen in one day. In the morning, you can get 72, and as it gets hotter at noon, it could easily get 92. So it is now 20 degrees more, so you lose 12.9% or 1.8% reduction in your productivity, in the not productivity, in the force your engine, in the usable power your engine can generate. Okay. All right, and those two could be combined. You could be working in high altitude and high temperature. Then you should consider the reduction separately. Okay, the coefficient, remember I told you in the first or second slide that I will talk about coefficient of traction. So coefficient of traction is depends, is a factor by which the total weight on the wheels or on the tires or tracks should be multiplied, okay? So we need this guy. We actually need this guy to find the usable power, okay? We are interested to find the usable power. For that, you need to know the coefficient of traction and the weight on powered running gear is given to us. I mean, that is the weight of the machine, right? So that's a piece of data, a piece of information that is almost always available. So if you have the weight of the machine and if you multiply it by the coefficient of traction, you can get the usable power. Okay, so weight distribution on powered running gear. This is a picture from the book. So for track type tractor, where there are no tires, use total tractor weight, okay? So we want to know in the previous equation, what kind of weight should we use? So if you're working with a tractor, then you should consider the total tractor weight. For four-wheel, it is 40% of the vehicle's gross weight. And for two-wheel, it is the 50% of vehicle gross weight, okay? So you should not always just put the gross weight of the vehicle in the equation. First, you should look at the type of the machine, and based on that, you should make a decision if you are using the total, the gross weight. Well, you will do that if you're working with a tractor, or if you're using 40% of that weight or 50% of that weight. All right, here is another example. A rubber tire tractor has a total weight. Okay, so the weight is given to us. On its driving wheels, the maximum rim pull in low gear is this much, okay? If the tractor is operating in wet sand with a coefficient of traction of this much, what is the maximum possible rim pull, okay? So the maximum possible rim pull is asked. In part B, if the same tractor is operating on dry clay with a coefficient of traction of 0.6, what is the maximum possible rim pull prior to slippage of the wheels? Let's do them one by one. So you can still see the problem on top right, above my picture, my video. So here, in part A, problem was asking for if the tractor is operating in wet sand with a coefficient of traction of this much. Okay, what is the maximum possible rim pull? So in order to do that, you simply multiply. So remember, we said for rubber tired tractor, okay, has a total weight of this much. Okay, so for this, you should consider the coefficient of traction, which is 30%, and you should consider the weight of the vehicle, which is 18,000 pounds. So this is the this is the RIMPL you can get from this machine. In part B, it is saying if the same tractor is operating on dry clay with a coefficient of traction of 0.6, what is the maximum possible RIMPL prior to slippage? Okay, so now you got a different coefficient of traction, which is better than the previous one. So you see it is wet sand. Moving on a wet surface is more difficult than moving on a dry surface, right? So here the coefficient of traction is bigger than the previous one. So if you do the math, you simply do 0.6 multiplied by 18,000 power, which is the weight of the machine. The answer you get is 10,800 pounds. That's the maximum RIMPL. As you can see, you can get a better RIMPL on a dry surface compared to a wet surface. Okay. For this surface, the engine will not be able to cause the tires to slip. Okay. Thus, the full 9,000 pounds of RIMPL is available to do work. Okay. All right. So, another exercise, a wheel tractor scraper is used on a road project. When the project begins, the scraper will experience high rolling and great resistance at one work area. The RIMPL required to maneuver in this work area is 42,000. So the RIMPL here is given to us. In the fully loaded condition, 52% of the total vehicle weight on the drive wheels. Okay, so this is the coefficient of traction that is also given to us. Sorry about that. The fully loaded vehicle weight is this much. So weight is given, RIMPL is given, and also Okay. In the fully loaded, 52% of the total vehicle weight is on the drive wheel. Okay. What minimum value of coefficient of traction? Okay, so this guy is not 52%, is not the coefficient of traction, because that is asked by the problem. So the weight is okay. So it is saying 50% of the total vehicle weight is on the drive wheels. What we care about is the load on the wheels, okay, for a wheel tractor, okay. We do not necessarily need the weight of the equipment. We want the wheel, the load on the wheel, okay, the weight that the wheels are carrying. So they're carrying 52% of the total vehicle's weight. This is the total weight, and this is the percentage. 52% is what the wheels will carry. So this guy is telling us how much weight is on the drive wheels. So in the next part, by having the RIMPL here, remember RIMPL, what was the RIMPL? RIMPL was coefficient of traction multiplied by the weight of the machine, okay? The weight on the tires. The weight on the tires multiplied by the coefficient of traction would give you the RIMPL. What would give us the RIMPL? Here in this problem, weight is known, RIMPL is known, coefficient of traction is unknown. So by dividing the RIMPL, which is 42,000, okay, here, by dividing the RIMPL by the weight, you can find the coefficient of traction. Okay, all right, last slide. Altitude's effect on usable power. As you can see, For most of the altitudes, it's still 100%. Yeah, this is based on percent. But for some altitudes, some of the machines lose a part of their power. For example, scraper at an altitude of 5,000 to 7,500 feet, they lose 5%, okay, of their power. In other words, 95% of their power is available, okay. Or, for example, loaders, the lowest number here I can see is 80%, right? So, for example, scrapers lose 20% of their power if they're working in a very high altitude. All right, this completes our part 3. This is the first time we're doing a chapter in 4 classes. That means we need another class to finish this chapter, and we will have a quiz next Monday from this chapter. Okay, so next Monday we start the class with a quiz. The quiz will be similar to the previous quizzes we have had, but it is online. Okay, so that's it. I hope you guys have learned today in our virtual class and with your smiley faces. All right, I'll see you guys on Friday.